Okay, last time we completed energy and spontaneity, and also we completed entropy. Today we want to start another point, that chapter thermodynamics, that is Gibbs energy. But before that, you know that for a spontaneous process, delta S should be greater than 0. For process to be spontaneous, delta S should be greater than 0. Means whenever delta S total is greater than 0, delta S total is greater than 0, then process is said to be spontaneous. Whenever delta S total is less than 0, process is non-spontaneous. And whenever delta S total is equal to 0, process is at equilibrium. You know that delta S total means delta S system plus delta S surrounding. So whenever delta S total is greater than 0, last time we studied, process is spontaneous. Whenever delta S total is less than 0, process is non-spontaneous. And when delta S total is equal to 0, then process is said to be at equilibrium. But you know that here we are more interested in system than surrounding. We are more interested in system than surrounding. Means here system means reaction mixture. System means reaction mixture. So to find out the spontaneity of the reaction, scientist Gibbs given another thermodynamic property that is called as Gibbs energy. Denoted by capital G. So how Gibbs energy is defined? That is, Gibbs energy is defined by the equation, that is G is equal to H minus T S. Here this is called as equation number 1. So according to Gibbs energy is defined by the equation, or Gibbs energy capital G is equal to enthalpy H minus temperature into entropy. But as you know that enthalpy H, entropy S, both are state functions. So G, that is Gibbs energy, is also a state function. Okay, change in Gibbs energy is given by the equation. Delta G is equal to delta H minus T delta S. All this as equation number 2. Now you know that we want to know Gibbs energy and spontaneity. You know, energy change accompanies in a process is given as delta S total is equal to delta S system plus delta S surrounding. But you know that we are more interested in system than surrounding, and this controversy was solved by scientist Gibbs, and he developed another thermodynamic property that is called as Gibbs energy. So here you know delta S total is equal to delta S system plus delta S surrounding. Here it is important to know that we can write this equation as like this: delta S total is equal to delta S plus delta S surrounding. So here subscript system that refer to system is dropped here. Subscript system is dropped here. Now we want to know, that is, what is the relation between delta G and delta S. So we want to know what is the relation between delta G and delta S. As you know that delta G change in Gibbs energy, delta S change in entropy. So according to second law of thermodynamics, delta S total greater than 0 for a process to be spontaneous. Last time we completed example for this. So total entropy of a system and surrounding increases in a spontaneous process. That is the second law of thermodynamics. And you know that we can write this as equation number 3, and as you know we can write here delta S surrounding is equal to minus delta H upon T. What this equation indicate? All this as equation number 4. Here it is important to know that substituting this equation 4 in equation 3, what we get? We get delta S total is equal to delta S is equal to delta S minus delta H upon T. Delta S total is equal to delta H upon T minus delta H upon T. Here, what this minus sign indicate? That is change in enthalpy. Change in enthalpy of the surrounding is minus delta H. The surrounding is minus delta H. Now, call this as equation number 5. This is called as equation number 5. Here it is important to know that delta S total is expressed in terms of the properties of system alone. That's why rearranging equation number 5 we get what we get. After rearranging equation number 5 we get, that is T delta S total is equal to delta H minus T delta S. All this as equation number 6. You know that substituting this equation number 6 in the previous equation number 2, we get delta G is equal to minus T delta S. Delta G is equal to minus T delta S. So from this equation it indicates that Gibbs energy change decreases in the spontaneous process. That's why we can say finally that this equation number 7 indicates that Gibbs energy change decreases in a spontaneous process. Here, you know that for a process to be spontaneous, last time we completed, delta S should be greater than 0, delta S less than 0. Whenever delta S is greater than 0, process is said to be spontaneous, and when delta S total is less than 0, process is non-spontaneous. and whenever delta S total is equal to 0, process is at equilibrium. But from this equation, that is delta G is equal to minus T delta S total, it is clear that for a process to be spontaneous, delta S total greater than 0, delta S total greater than 0, and here delta G is less than 0, delta G is less than 0 for a process to be spontaneous, for a process to be spontaneous. Second point, that is delta S total less than 0 and delta G greater than 0 for a process to be non-spontaneous. Here, third important point, whenever delta S total is equal to 0 and delta G is equal to 0, process is at equilibrium. So you know that when we started energy and spontaneity, what is the criteria of spontaneity? First of all, we say that exothermic reactions are spontaneous, but it is not true. It is found that endothermic reactions are also spontaneous. That's why another property developed, that is called entropy. And you know that the entropy change for a process is whether it is positive or negative. We cannot decide the spontaneity from the change in entropy. That's why from the Gibbs energy change discovered by scientist Gibbs, that is called as Gibbs energy. From that Gibbs energy we can decide the spontaneity of the process. So these are the three important points. Whenever delta S total is greater than 0, at that time delta G change in Gibbs energy is less than 0, then and then only process is spontaneous. Second point, whenever delta S total is less than 0 and delta G is greater than 0, process is said to be non-spontaneous. And whenever delta S total is equal to 0 and delta G is equal to 0, process is at equilibrium. Now, next point we want to know, that is temperature of equilibrium. Next point, temperature of equilibrium. Next point, temperature of equilibrium. So here, temperature of equilibrium, you know that from the equation delta G is equal to delta H minus T delta S. Delta G is equal to delta H minus T delta S. So we can write the equation T is equal to that is delta H upon delta S, delta H upon delta S. So from this equation we can decide at what temperature the reaction is spontaneous. That is called as temperature of equilibrium. Now, Gibbs, last point of this chapter, that is the Gibbs function and equilibrium constant. Gibbs function and equilibrium constant. Last point, that is Gibbs function and equilibrium constant. Gibbs function and equilibrium constant. Gibbs function and equilibrium constant. So here you know that Gibbs energy change for a chemical reaction is given by the equation delta G is equal to delta G0 plus RT log of Q plus RT log of Q. Here delta G means Gibbs energy change, Delta G0 means standard Gibbs energy change. R stand for gas constant T temperature in Kelvin. Q stand for reaction coefficient. Here it is important to know that when we write one general reaction, that is A plus B react to give C plus D, Here small a, small b, small c and small d. These are the coefficients of reactant and products respectively. We taken here general reaction. What we are going to study? Gibbs function and equilibrium constant. You know that from this equation we can write, that is for this reaction we can write delta G is equal to delta G0, delta G is equal to delta G0 plus RT log of Q. Here Q stand for reaction coefficient, that is equal to delta G0 plus RT log of, that is log of concentration of C raised to C, concentration of product D raised to D upon concentration of reactant A raised to A into concentration of reactant B raised to B. You know that whenever reactant and products are in aqueous medium, we can write this equation. Whenever these reactants and products are in gaseous state, then we can write here log of QC as like this. Here, whenever these reactants and products are in gaseous state, then we can write delta G0, or this equation is for reactant and products involved in concentration is given or in aqueous medium. Whenever reactants and products are in gaseous state, delta G0 is equal to RT log of QP, that is equal to delta G0 plus P stand for pressure here, RT log of concentration of pressure of C raised to C, into pressure of B raised to D coefficient, pressure of A raised to A into pressure of B raised to B. So here it is important to know that this equation then we can write, that is this equation may be written as like this, that is 0 is equal to delta G0 plus that is RT log of Kc, or 0 is equal to delta G0 plus RT log of Kp. You know that when we write, or this equation may be written as like this, delta G0 is equal to minus RT log of Kc, or delta G0 is equal to minus RT log of Kp. You know that the same equation to the base 10 can be written as like this, delta G0 is equal to minus 2.303 RT log of Kc to the base 10, or delta G0 is equal to minus 2.303 RT log of Kp to the base 10. So this is about the Gibbs energy. Later on we will solve the problems based on Gibbs energy and entropy in next lecture. Thank you.